Hello, I'm Brendan Kelly and this is Carter Huffman, and we both work at Modulate creating voice synthesis models. Today we're going to talk about developing and running neural audio in constrained environments. And to start off, here's a quick audio test.
Welcome to developing and running neural audio in constrained environments.
So as you could tell, that was me. So the objective of this talk is twofold. First, to run through some practical lessons and tools we have picked up while researching how to effectively train speech synthesis models. And the second objective of this talk is to discuss some of the challenges and techniques required for getting this type of speech synthesis technology real-time in games. We will start off with an overview of the neural audio models we use in our work. We use an autoregressive wavenet approach to train our initial speech synthesis model. This model is trained to take as input a raw audio waveform and predict the next sample of audio. So for example, in the top image here, the model would see all of the black audio samples and use all of them to predict what it thinks the next sample should be, shown in red. In order to generate a single sample, the model needs all of the previous samples, which mean we can't generate many samples in parallel. So what does this type of model sound like? I'll start off with showing some audio generated with a more traditional parametric approach.
The Blue Lagoon is a 1980 American romance and adventure film directed by Randall Kleiser.
Now I'll play the same speech through the autoregressive model.
The Blue Lagoon is a 1980 American romance and adventure film directed by Randall Kleiser.
As you can hear, there is a pretty obvious improvement. One of the problems with this type of autoregressive approach is that for 24 kilohertz audio, we're going to have to make a full pass through our model 24,000 times a second, and that's just usually not tenable. This type of autoregressive model ranges from medium slow to extremely slow during inference, and so we can't use it easily for real-time applications. So if we can't generate audio one sample at a time with this approach, what if we generate them all in parallel? In this case, the model is not predicting the next sample of audio, and so it's a bit trickier to train this type of model. Following on from some recent research, we can train a new parallelizable model by using the autoregressive model from the slide before. The idea is that the autoregressive model can look at the generated samples and see what the next sample should be. Then that the autoregressive model can send those probabilities back to the parallelized model and tell the model how to generate better audio. In reality, it's a bit more complicated, but this is the gist of the parallelized approach. So now that we have an audio synthesis model that can run in real time, what can we do with this technology? First, we can train the model to produce speech that sounds like anyone we record from. In this particular case, we have some audio from Serena, and we teach the model to sound like Serena through the introduction of an adversary. The adversary is a neural network which listens to real speech from Serena and also to speech from our model and learns to tell the difference. It then propagates the Serena-specific features it used to tell the difference back to the model, which updates itself to not make the same mistake again. Iterating over the course of a week or two, the adversary gets really good at distinguishing between the model and real audio, and the generator also gets really good at mimicking real audio from Serena. The final form of this type of model is a master model, which can produce audio which sounds like anyone from our dataset. As an example, here's a set of audio clips where we take the input speech and produce that speech in the voice of another speaker. Here's the input speech.
Modulate voice skins let you customize how you sound.
Here's that speech output in another speaker's voice.
Modulate voice skins let you customize how you sound.
And here's the same in a different voice.
Modulate voice skins let you customize how you sound.
And so you can see that, or you can hear that the content of what is being said is the same for all three clips, but the voice profile is significantly different. Now I'd like to talk a bit more about the challenges that we encounter during training. So the first problem is a problem everyone runs into. These models are very large and require a long time to train. On a single V100 GPU, our model takes approximately 25 days to train from start to finish. This long training time is becoming increasingly commonplace for state-of-the-art models, with many requiring distributed training across many GPUs to finish within a reasonable amount of time. In order to cut down on the time and money required, two straightforward things to do are: one, use a pre-trained model to jumpstart your training. Alternatively, you can use an existing model and fine-tune that model for your particular dataset or training scheme. This reduces our training time significantly and lets us focus directly on our experiments. Even after cutting down on training time, you still need significant resources to do anything at all. If you're a startup in our position, there are numerous cloud programs that offer credits that make this a lot easier and a lot more affordable. We'd like to give a special shout out to Founder Friendly Labs, which helped our company significantly in the early stages. So let's say that we have training, or we're training our models less, and we have some sponsorship so that we can easily train some models. The next step is optimizing the usage of GPU time by killing experiments early based on heuristics. When training, we watch a lot of statistics about our model, and we find correlations between really bad performance and different statistics during training. There are many types of these statistics, and they will highly depend on the model architecture and problem domain, but the idea of using these types of correlations to kill experiments early can be applied to any problem. I'm not going to go through every statistic that we use, but only focus on the dead ReLU statistic during this talk. There are more linked in the slides. Here's a ReLU unit. It's one of the simplest nonlinearities you can use within a network. And if the signal is positive, the ReLU unit passes the signal through, and if it's negative, the ReLU unit kills the signal. Towards the end of our network, the high-level features generated by our model are passed through one last ReLU before a final convolution layer. Different sets of these features are active for different input data. Some final features are mostly used for input data, or female input data. Some final features highly depend on the target speaker profile. And we found that sets of these ReLUs tend to be dead no matter the input to the model or the target speaker profile. What this means is that the final layer isn't using the full capacity of the network to produce an output. It's only using some fraction of the feature space. We've found that the number of dead ReLUs is a good indicator of the health of our models. If too many are dead, this generally correlates with poor model performance. For a training run, here's a plot of the number of dead ReLUs over time. As you can see, the number of dead ReLUs spikes in the first third of training and then slowly levels off to around 200 by the end of training. We have found that the spikes towards the end of training, where sets of ReLUs suddenly come back online, is a particularly problematic phenomenon during training. One reason that this phenomenon is problematic is that when a ReLU becomes dead, it stops being optimized directly. And so when it's reactivated, all of its weights are out of date, and the resulting gradients throw the model out of whack. If the vast majority of the ReLUs died, then this is highlighting that the effective model capacity is much less than the potential model capacity, and this is a major problem. The dead ReLU pattern changes drastically for different model architectures and for different experiments that we run, so watching this plot for absolute numbers and behavior changes over time can give us qualitative insights into the behavior of the model. Using these types of statistics, we can save a lot of training time, often killing experiments after a few hours or a day. Using these types of correlation also allows us to iterate faster by requiring far less time to analyze model performance. Now, how do we evaluate these models? How do we actually analyze model performance? A problem with research in general is evaluating a solution to a problem. With neural networks, we come up with a hypothesis, train a model based on that hypothesis, and then generate statistics and metrics for that model. There are a few types of metrics to use in generative problems, such as audio synthesis. We can use training losses. Training losses are a bit difficult to weigh against each other as we can have multiple losses, and each doesn't always correlate with performance. We can use other neural networks to generate scores, but these neural networks the performance of these neural networks are highly dependent on their data set and the task for those evaluation nets. We can also use human scores to score the output of our models, but these methods are pretty slow and costly and difficult to target specific aspects of media or different dimensions which we're focused on. So this leaves us with the question of how do we close the loop and iterate on our ideas quickly? So instead of using those losses, we use our own assessment protocol. We design this interface with a specific goal in mind, and that's to understand how an experiment changed a model's behavior compared to a baseline behavior. Here's an image showing the entire interface. The main draw of this type of tool is that it facilitates the comparison of different models along different dimensions. Additionally, This type of tool helps simplify collaboration across a single team and even across different teams or the entire company. This type of tool helps create complex comparisons between our models in about 15 minutes and helps us collaborate across our team. For more information, see the links in these slides. Equipped with these tools and strategies and some hard work, it's possible to make models on a small team with a tight budget. And so with that, we will move on to the next section of this talk with Carter.
Fantastic. Thanks, Brendan. So we've got this model that we've trained, and now we want to use it in our game. As you might expect, we're going to run into some challenges when trying to deploy these models. The first question we need to figure out is where and when are these models going to run? So in many cases, you'd really like to run your neural network before you ship the game during development in order to create assets that you can statically bundle in with your game client. However, in some cases, like when you want player interaction, that's impossible. So maybe you try to run the model on the cloud, where your players send off an input, your neural network computes, and then sends back a result. This can be really great if you can use the power of cloud-based hardware to do all this really heavy neural network lifting, but sometimes you have constraints that make that untenable. So for example, in our case, we're building voice skins, which swap out your vocal cords digitally so you sound like someone else as you're talking in voice chat. In that scenario, it's really hard to experience a voice skin unless you can actually hear what you sound like, so that you know what voice is being broadcast to others. That's really cool, but this is running in real time as you're talking, and so if you take that voice that you've generated and you pipe it back into your ear, you get this weird echo effect that makes it difficult to form coherent sentences, which is obviously bad. If the total round trip latency from when you speak to when you hear that echo is under 30 milliseconds, however, then it starts to sound just like a natural part of speech, and that disruptive echo effect goes away. So we really, really want to keep our voice skin round trip latency under 30 milliseconds or so. That makes a hop out to a cloud server and back totally impossible. Furthermore, if your game is running offline, or if, say, your voice chat is going directly peer-to-peer, it's a really hard sell to put a cloud server in the middle of that so that you can run your neural networks efficiently. So in some of these cases, you have to actually run your neural network on device while your players are playing a game. And of course, if you try to do that, you're going to run into a bunch of constraints. The most prevalent of these is resource consumption. So when you're training these models in order to get good results, you will make a model that has millions of parameters, and it's using these parameters in matrix multiplications, which are really computationally expensive. And when you're training, you can do all of this on a really big, beefy GPU. You can take up all of your video memory and train these models for weeks. However, when you're trying to run in a game, a player might be playing on a desktop with a solid GPU, or maybe on a laptop, or on a phone, or on a console, etc. And in all of these different cases, you have a lot less compute available to run your neural network inference. So as a comparison, our master model that maps any voice into any other voice, when run on a GTX 1080 for inference, gets almost 10 times real-time throughput. But even if it runs on a relatively beefy CPU, it doesn't even break the real-time threshold, so it wouldn't be able to keep up with you as you're speaking. So that's definitely not going to work. Furthermore, I was mentioning your players might be playing on various different devices, and all of those have different compute capabilities. One thing you don't want to do is limit people with a significant amount of compute capability to the same amount of neural network quality that maybe someone with a less performant device is using. So for example, you might ship one model to someone running your game on a phone that is able to be used on a phone in real time, based on limited compute and power constraints, but you might want to ship a different model to someone running on a desktop with a lot of compute available. So how do we solve these problems? It turns out we can solve both of those things with one technique, distillation. So you can see on this slide, we've got on the left side, there's this big master model that's trained with adversarial training and does all these complicated things. But at the end of the day, it takes an input audio clip and maps it to an output audio clip. We can take those input-output pairs and use that to do supervised training on a much smaller distilled model where we can tune the number of parameters that the distilled model uses based on the compute constraints of the hardware we're shipping to. So for example, if we want to serve all these different devices, we could ship a small distilled model to phones and a large distilled model for desktops. We get something else really cool from distillation in that we can shed unneeded capacity. So when we're training this big master model, for example, we're mapping any voice to any voice, but when you're using a voice skin, you only need to sound like one voice at any given time. Having around that capacity to synthesize all of those different voices takes up a bunch of parameters that are wasted if you only need to model one particular voice at runtime. So we can actually train a bunch of different distilled models, each targeting different voices, and trade development time, running these models in parallel, for runtime when we're actually trying to run on device, using a smaller distilled model targeting only one output speaker. And when we do this, we actually find that the quality of the output audio isn't too severely affected, even if we're drastically reducing the number of parameters. So we'll look again, here's the performance of the master model on an i7-6700K CPU. It's got 1.6 million parameters and it's not breaking the real-time threshold. We've got a couple different distilled models that we've trained, a high quality, mid, and small size model, and each of them easily clear the real-time threshold on that same CPU. And furthermore, the quality of the audio isn't severely affected. So here's a clip from the master model.
My name is Carter Hoffman, and this is a test of timbre transfer.
And that same clip from the mid-sized distilled model.
My name is Carter Hoffman, and this is a test of timbre transfer.
Different, but not a massive change. So awesome, we can solve some of these problems through distillation, but we're still going to run into more constraints. One of those constraints is optimizing for latency in particular, or other constraints that aren't throughput. So if you're going to actually deploy your neural network on device in the game client, you're probably going to use an inference framework such as TensorFlow Lite or others that are mostly optimized towards maximizing throughput at the expense of everything else. But if you're in, say, a real-time audio scenario, you're very concerned about maximum latency for converting any individual audio frame. If you go over a certain amount of latency for that frame, you might miss the next audio frame that's coming in and experience an audio glitch, which is really unpleasant. So you might actually be more concerned optimizing for maximum latency than you are optimizing for throughput. Furthermore, especially in, say, a real-time audio context, you might have to avoid entire classes of operations. So for example, anything where you might block on the audio thread or do memory allocations, which means the operating system has to get back to you with that memory, you're potentially waiting longer than the audio frame time and once again missing that frame, causing an audio glitch. So if you just try to use a standard inference framework that isn't worried about whether or not it does memory allocations, you end up with audio glitches like this.
My name is Carter Hoffman, and this is a test of timbre transfer.
So we can't ship that. What are we going to do? Well, it turns out a really good solution is to just write your own custom inference code. So you can just write out your neural network inference logic in C++ and manually avoid memory allocations or blocking operations. In our case, we run entirely single-threaded on the audio thread while you're running your game. We use vectorization and fused multiply add instructions in order to do all these matrix multiplications very efficiently. And you can take advantage of a bunch of resources to help you do this. So for example, we use Eigen, a C++ header-only matrix multiplication library that already does a ton of optimizations on a per platform basis. So we don't actually have to worry too much about how we're optimizing for specific devices. We get a lot of that for free by using these libraries. Furthermore, if you're writing your own custom inference code, it makes it very, very portable. You can cross-compile to any platform you want to. And furthermore, you get an added bonus that you integrate easily into a variety of different tools. In our case, we found that our custom C++ library slots really easily into various digital audio workstations using a framework called Juice, which lets us collaborate really, really effectively between our machine learning team and our audio team, because our machine learning team can generate a new model and we can ship it directly over to our audio team, which plugs it into their DAW and starts working with it. So that kind of collaboration is really, really useful and is available to you if you're writing this custom inference code that's very portable. So you're writing this custom inference code, and one of the often claimed problems with doing this is it might take a lot of time to write all of this yourself. And furthermore, if you change any of your logic in your machine learning model, you then have to change your inference code. But actually, the distillation technique that we mentioned beforehand can avoid a lot of these issues. So in our case, most of our machine learning iteration is changing this master model, changing the loss functions, changing the data, changing the architecture, etc. However, when we go to distill from that master model, the distilled model architecture stays pretty much constant. So by distilling from these different master models into the same exact architecture, those distilled models are just different weights on top of the same neural network architecture, and they plug straight into the custom SDK. In fact, our custom inference code hasn't changed substantially in over a year, even though we've iterated massively on the audio quality of these master models in a variety of different ways. So writing your own custom inference code might in fact be tenable. If you're going to do that, especially for audio, there's a couple tips to help you do that effectively. One is many different audio frameworks, like these digital audio workstations, etc., will expect you to adapt to various sample rates and various frame sizes. You can be robust against that by bundling in your own sample rate converter. Secret Rabbit code, for example, is really, really good. We just bundle that straight into our SDK. And if you pre-allocate a bunch of memory beforehand, you can use subsets of that memory while you're doing inference on various audio frame sizes. So if you take that effort, you'll be pretty robust to what different digital audio workstations or other audio environments will expect. And so once again, you can sort of put your custom inference code anywhere. Furthermore, especially around neural network generated audio or neural network effects, logging is really, really important. It's pretty difficult to separate out what errors might be coming from something going on earlier in your audio chain versus your neural network versus later on in your audio chain. And so including real-time logging of inputs and outputs to your neural network is super important. We talk more about this in a blog post. It's a little bit tricky to log this audio without introducing blocking operations, but it's super, super valuable, so I highly recommend you do it. So we've gone through all of this effort to write this custom inference code, and what is our result? We can run our neural networks real-time on audio while avoiding any blocking operations that would cause audio glitches.
My name is Carter Hoffman, and this is a test of timbre transfer.
Fantastic. So thank you guys for listening. We'll wrap up really briefly. So even if you're a small team trying to do neural network audio synthesis, you can train and deploy these machine learning models. You definitely want to take advantage of pre-training when you can to drastically reduce the amount of time you're training these models. Prune your experiments by watching various informative heuristics so that you can stop experiments that won't be useful long before they take up too much time and resources. And spend some time designing good QA tools that directly optimize the objectives you're looking for. That'll help you iterate really effectively and also communicate with the rest of your team. When you actually go to deploy these models for your game, if you have to run in real time in the game client, definitely optimize with distillation in order to trade various compute resources for quality from your neural network, depending on the kind of hardware that your players have available. And don't be afraid to write your own custom inference code. It lets you optimize for the various objectives that you need to, while potentially avoiding some of the downsides by coupling it with distillation. So I highly recommend you give that a try. Thanks so much for coming to our talk and for watching. Thanks especially to Olivier for organizing the ML Summit. Thanks to GDC for having us. And as we mentioned before, thanks again for Founder Friendly Labs for their early support. Hope you enjoyed our talk. Thanks.